talked about the geodesic equation, and I gave basically two formulations of that equation. One where we are talking about a curve, parameterized curve, with some arbitrary parameterization that I'm calling t. So that can be anything at one, anything at all. And when we're given that parameterization, the tangent vector is going to be is what I denoted t. And then the statement of the geodesic equation in that case is that the covariant derivative of that tangent vector is not going to be zero, but it's going to be proportional to the tangent vector. So that would be an example where, even though we're dealing with the geodesic, we don't have the property that the vector is parallel transported along the curve, and that has to do with the fact that we have this, parameterization that is sort of fluid and stretchable in all of this. So we end up with a vector, an acceleration vector that's proportional to the velocity. So that's for an arbitrary parameterization, but if we're using proper time, then typically the notation is that instead of using a generic t for the tangent vector, we're going to be using u, and we would call that the velocity vector of the curve. That now refers specifically to a derivative with respect to proper time. So now we fix the parameter to be specifically proper time. And then the statement of the geodesic equation in that case is that the acceleration vector in that parameterization is zero. And that's what we normally, deal with. But, as I indicated, there's going to be cases where this representation is more advantageous than the original one. And that's a case where we have also the sense that the geodesic is given in terms of a tangent vector that's parallel transported on the curve. That's the meaning of that equation here, but that's only true in that very specific parameterization. Now, we don't have to restrict ourselves to proper time parameterization, because if I were just to rescale proper time by a constant, that equation would not change. And if I, rescale the proper time parameterization, that equation is still satisfied. If I change it by a constant, obviously that doesn't change anything. So even though we tend to restrict ourselves to proper time here, we have an invariance of that equation under a more general rescaling of the parameter, and any parameter that satisfies, that's related like this to proper time is called an affine parameter. And that's language that I'll probably use in later portions of the course. Okay, so that summarizes the morning. And the other thing that I'll say is that, well, we can unravel this notation here. We can remember that the covariant derivative, I'll use the restricted formulation here. The covariant derivative is really shorthand for partial derivative or ordinary derivative with respect to proper time plus Christoffel terms. So we can write it like this. And I can even unravel the notation some more by substituting what we mean by u. And what we get then is the formulation of the geodesic equation that tells us that it really gives us a system of second-order differential equations for the coordinates as a function of proper time. So if we have to find the geodesics of a given space-time, at some point, well, we want to solve that equation, and it's going to be a second-order differential equation for the coordinates as a function of proper time. And then, because it's a system of second-order equations, you have to provide two pieces of initial data, namely the initial position and the initial velocity at that point. And once you have this, you have a unique solution for times beyond that. So that's the usual statement of the geodesic equation. And then if you look at it and take it a little bit too literally, you're going to say that, well, this is like the acceleration, and this is like the gravitational force acting on the particle. We tend not to use those words because they're very ungeometrical. What we're really dealing with here is a perfectly nicely defined geodesic in space-time, and that gives us an extremum of proper time, at least for short enough geodesics. Okay, So we're good with that? Any questions at this stage? Okay, so that's more or less where we were. And what I want to do this afternoon is, first of all, I'll combine those two notions of killing vector and geodesic equations to talk about conserved quantities. I'll do that first, and then I'll introduce curvature. So that's going to be the last central ingredient that we're going to need to, for the course. So I'll introduce the Riemann tensor and talk about this. And then if I have time, we'll do a few more things. Okay, so conserved quantities. So let's assume that we have a curve with a tangent vector that I'm going to, so a parameterized curve in terms of proper time. So I'm going to restrict myself to proper time parameterization, or at least an affine version of that. And assume that we have a geodesic parameterized by proper time. So we have the geodesic equation. And I'll write it in the form that I had over there, with a 0 right-hand side. Suppose that we have that, and suppose that we have at least one killing vector. And here it could be any one of those killing vectors that we've talked about. It could be the one that gives us invariance along time if we're dealing with the static spacetime, or invariance under rotations if we're talking about an axisymmetric space-time. But if we have, those two things, then we have automatically a conserved quantity. And what I mean by that is that, well, I'll define it first. If we take the scalar product between the velocity vector and the killing vector, then the claim is that this is not going to change along the curve. And that's what we mean by conserved quantity. The motion proceeds, but that quantity doesn't change with it. And depending on the nature of the killing vector, this may represent energy, it may represent angular momentum, it may represent linear momentum. There are various possibilities like this. But regardless, when we have a geodesic and a killing vector, we automatically have a conserved quantity. And that's the nice connection that we always have between a symmetry and a conservation statement. So Noether's theorem is all behind this. That's one particular manifestation of this connection, which is always nice. Okay, so the proof. The proof is actually pretty simple. So I'm going to rewrite the statement in terms of covariant derivative, because we're dealing with a scalar quantity. So there's no distinction between ordinary derivative and covariant derivative. And I'll just plug in what I mean by C. So it's just that. And I'm going to just evaluate this derivative. So we have a product. So the first term we're going to get will vanish all by itself. And the second term we're getting will be the covariant derivative of the killing vector with respect to the curve. So by virtue of the geodesic equation, all of that vanishes. And the promise is that, well, the second term will vanish all by itself as well. So I'm going to rewrite this in a slightly different way. So I'm just going to change the position of the indices here, which I can do because I can always freely use the metric inside a covariant derivative without getting into trouble. And then I'll just rewrite this as a derivative of a vector field in the direction of the tangent vectors of the curve. So I'm going to write it like this. And then in principle, I could declare the calculation to be done, because we remember that this gradient here is antisymmetric. This tensor in front is symmetric. So this is something that's antisymmetric with respect to a swap of indices. This is symmetric under a swap of indices. And whenever you're multiplying a symmetric tensor with an antisymmetric tensor, you're guaranteed to get 0. So I could just claim this and say that this is 0, But maybe you feel a bit insecure about this, so I will, make a few extra steps to make this completely explicit. So we're not going to leave it just as that. But it will turn out to be 0. So what do we have? So I'm going to write this as half of itself plus half of itself. But in the second half of itself, what I'm going to do is to rename alpha beta and rename beta alpha. So I can always rename dummy indices that are being summed over, and I can just, do this, rename my two indices and change their identities this way, and it doesn't change anything about the outcome. So I can express it like this. And so I'll do that. And then I'll factorize the 1/2. I'll factorize the two factors of the velocity vector. And then what's left over is this gradient plus this gradient. And now we recognize that as being 0 by virtue of Killing's equation. So we get 0 as promised. So, the shorthand to this would have been to conclude here, this is antisymmetric, this is symmetric, therefore it's 0. We could have stopped there, but sometimes you need to see a little bit more of the work to be fully convinced. But in both cases, we could actually rely on the symmetric property, antisymmetric property, because we ended up producing here something that ended up being factorizable. So we really, exploited that symmetry property in the position of the indices here in the course of that calculation. But anyway, I think it comes out, and we do get the statement that whenever we have a Killing vector and a geodesic, we get a conserved quantity. If you're curious about the role of the proper time parameterization here, it turns out to be pretty important that we get a conserved quantity only when we're using proper time parameterization, because we needed this to be 0. If it were not 0, then we would get a non-zero term over here. We would get, the kappa that multiplies the t that multiplies the xi. So we would end up with an equation that says that the derivative of something is given by kappa times something. So we would get something that would give us an exponential behavior as opposed to 0, as opposed to a constant behavior. Anyway, so as an exercise here for you, you could try to see what changes if we go back to an arbitrary parameterization. And the statement is that in that case, C would not be conserved. C would be something that could be solved for, and you would get an exponential solution for it. Okay, so that's the idea. So we have a very clear connection between a symmetry and a conserved quantity. So that's always very pleasing to see this, and that's the reason why we care so much about symmetries in a space-time, because if we're interested in working out the behavior of geodesics, the first thing you'd want to know is to understand the symmetries so that you can identify all of those conserved quantities. In some fancier spacetimes, you end up having symmetries that are not manifested through a Killing vector, but there are variations of the theme where we have Killing tensors and conserved quantities associated with that. And it's a bit of a more complicated story, and I won't go into it right now, but that's something that will come back when we talk about the Kerr solution. Turns out that there are conserved quantities associated with geodesic motions in Kerr that are not associated with a Killing vector, but associated with something more complicated. That's called a Killing tensor. So that's something else that we'll probably talk about at some point.
Can I have a question?
Yes, please.
Is there any systematic way to find the Killing vectors or Killing tensors of a space-time?
Only in the sense that what you're supposed to do is to go back to that equation. And what you would do is, okay, here's the metric, here's the formulation of that equation in that coordinate system for that metric. And you would go about finding all the solutions you can find to that equation and hope that you found them all when you're done. So it can be a very complicated task. As we talked about this morning, sometimes it's obvious because you see that the metric doesn't depend on time. there's a killing vector, but sometimes the killing vectors are a bit harder to find, a bit harder to identify, and bottom line, you have to go and look for them through solutions to that equation. So that's a game that you can play if you're an applied mathematician and you're good at solving partial differential equations. And for us physicists, you better hope that somebody did that before you, and you can rely on their results and make use of them. So yeah, so typically those are difficult equations because all the components are coupled together. You have partial derivatives. It's a complicated system of equations, and you have to be pretty good at this sort of thing if you're going to find all the solutions you can find. Okay, so just thanks for the question. That's a very good question. So as an example, we can go back to that spherically symmetric spacetime, static spherically symmetric spacetime that I talked about before. Where we had identified 4 killing vectors, but here I'll just focus on the 2 obvious ones. So if we have the first killing vector, I'll call it Xi with a T, giving us the symmetry in the time direction, then the quantity that's going to be conserved on a geodesic is going to be the thing that you would interpret as the energy of the particle. So there's a quantity that I will call E tilde, and that by definition would be minus the scalar product between the 4 velocity and that time killing vector. By the theorem we just formulated here, that's guaranteed to be a conserved quantity. But if you went and interpreted physically what this quantity means, well, it's actually the energy of the particle at measured at infinity, divided by the mass of the particle. So those conserved quantities, of course, typically have an interpretation in terms of the physics of the problem. And here, if you have a time translation symmetry, that conserved quantity will correspond to the particle's energy, and it's going to be conserved as the motion proceeds. And if the motion started out at infinity, well, it's literally going to be the energy that you would measure at infinity, and then that energy would be preserved as the particle goes deep into the space-time. The other quantity that we have like this for the other obvious killing vector, the one that corresponds to a rotation along the z-axis, that one corresponds. So the one is defined by the scalar product between the velocity vector and the axial killing vector. And that corresponds to angular momentum. So that would be the z component of the angular momentum, also measured at infinity, divided by mass. So that's just to make the point that those conserved quantities have an interpretation in terms of physical quantities, and those are very precious quantities to have at your disposal when you're trying to find solutions to the geodesic equations. And typically the way it works is that, well, you can go from a second order formulation of the geodesic equation to a first integral solution for all the coordinates if you have access to those conserved quantities. So they're very, very useful. So they're used whenever it's possible, whenever you have access to them.
May I have another question? Sorry.
Yeah, please.
How is it possible to define generators of time translation using this time-lag killing vector?
So you're asking how is it possible to define a generator of a time translation?
Yeah, time translation using this killing vector, time-lag killing vector.
Well, yeah. So I mean, so I would say that it's the killing vector itself that defines the time. So it's the time killing vector that we're dealing with here is really describing a translation in the time direction. So the integral curves of that killing vector are the flow lines along which nothing changes if you were to evaluate the metric along any one of those integral curves. So I would say that it's those killing vectors that are generating those symmetries. I'm not sure if that answers your question. I'm not sure if I got your question, but
it is there is no need for exponential here.
Exponential. Oh,
Yeah,
you're thinking of the action of Lie groups and generating of Lie algebras, generators of Lie algebras
yeah.
and things like that. Okay, yeah. So I don't think. I mean, so I think it's possible to connect those two languages into abstract differential geometry, but I don't think I'm gonna. I don't think I'm gonna go there. I wouldn't know what to do really.
Okay. Thank you.
Okay, very good. Okay, any questions about this? Okay, so basically the bottom line here is that we like killing vectors because we like those conserved quantities. We need killing vectors because we want to have all the conserved quantities that are there. And in order to talk about killing vectors, we have to talk about Lie derivatives. So it all brings all of that together. So, all of this tells us of the importance of these concepts when we do work in curved spacetime. Okay, so let's talk about curvature. So I think we all have some, so of course you've seen this stuff before, you know what a Riemann tensor is, you know that this is how we measure curvature in a curved spacetime or in a curved manifold in general. But I just want to go over that story again, define it mathematically, but also define it in terms of physical intuition. And, I think we all have a sense of what curvature is all about. So we know that the surface of the Earth is curved, but that a plane is not. So I think, it's all pretty clear, but the idea is, can we turn this sort of intuitive picture into a mathematical definition of the curvature tensor? And that's what I'm going to try and do here. And in fact, I'll define it mathematically first, and then we'll see how that mathematical definition can be used or can be ported to a more intuitive picture. So the mathematical definition is basically that it measures the failure of two covariant derivatives to commute. So the idea is this. So suppose that I take a covariant derivative of a vector first with respect to beta, so I'll write it in full notation, first with respect to beta, then with respect to alpha, and suppose that I do it in the opposite order. If we were dealing with a flat spacetime, we would find that irrespective of the coordinate system that we use, it would be obvious in Cartesian coordinates, but I claim it's going to be true in all coordinate systems. If we work this out in a flat spacetime, the answer is always going to be 0. But if you're not in a curved spacetime, it's going to be non-zero. So the curvature tensor is really a measure of the failure of the second partial derivative to commute. And, well, it's pretty clear that on the right-hand side, we're going to have something fairly complicated as an object because we already have 3 floating indices here, and we're going to need a 4th one because the result is going to be linear in A. And the outcome of this is going to be the Riemann tensor. And the statement is that, well, this, this failure of second derivatives to commute when it's acting on a vector like this is going to be linear in the vector. And it's going to be independent of first derivatives. And then it will involve an object that's defined geometrically. And that, by definition, or by the mathematical definition, is the Riemann tensor. So that's really the definition. And once we have this, well, we have, an ability to work out the left-hand side and make the left-hand side completely explicit. And because we're talking about covariant derivatives, there's going to be a whole bunch of gamma terms. And we can turn this statement into an explicit expression for the Riemann tensor, where it's pretty complicated. We get derivatives of gammas, and then we have gamma square terms So I won't bother putting down the indices, but I'm sure you've all seen those ugly, ugly expressions for the Riemann tensor in terms of the Christoffel symbols in a previous course. So, if you need to compute the Riemann tensor, that's typically what you would use. But the point is that, well, it's really defined in terms of, the commutator of covariant derivatives acting on a vector, and then the object that defines is a proper tensor because everything in that equation is a proper tensor. Okay, so that's how we define the curvature tensor, and it's called the Riemann curvature tensor. And then, we can play around with all the symmetry. So it's obvious that the Riemann tensor will be antisymmetric in alpha and beta because that's true of the left-hand side. It's got to be true of the right-hand side. So we have that symmetry. And then when we look a little bit deeper into it, well, there's also an antisymmetry in the first two indices. There's a swapping symmetry where we can send those indices first, send them next, and then that's another symmetry. And then there's a cyclic symmetry. So there's all sorts of symmetries that are present for the Riemann tensor that are useful to know because they can be very helpful in a computation. Anyway, I'm assuming that you've seen all of this before, and there's more details about this spelled out in the book, but I'm going to be happy with this definition for this discussion. So that's the commutator of derivatives acting on a vector. I could lower the index and we would get the action on a covector. I can generalize this to tensors. Basically, there would be a Riemann term for each index you have on the quantity on the left. And so all of this can be worked out. So I'm not gonna belabor those details here. But what I want to do, and that's really my purpose here, is to turn something which I would consider to be a mathematical definition, failure of second derivatives to commute, into something that reconciles us with that intuitive notion of curvature. And there are more than one way of doing this, but the way I'm going to choose is through the geodesic deviation equation. So that's where we're going next. And the idea is this. So what distinguishes a flat manifold from a curved manifold is the fact that if you start with two geodesics and they're parallel, if you live in a flat space, they're going to remain parallel forever. Whereas if you live in a curved manifold, even though they start parallel, they're going to either diverge or converge together in the course of the evolution. And that, failure to remain parallel is something that does match our intuition about what curvature is all about. So let's contrast the two situations. So we have a situation in flat space where we have, say, two geodesics, namely two straight lines. And if they start parallel, that's one of Euclid's axioms, they're going to remain parallel forever. So we can say that the relative velocity between the two geodesics is going to be, between the two straight lines is 0 in this case. And the relative acceleration between the two is also 0. So that's the situation for two straight lines that start parallel. But if we're talking about a curved manifold, for example, the surface of the Earth, the geodesics for the surface of the Earth, those are going to be the great circles. And I can launch one of those great circles here on the equator. And it starts out here at the equator, and we're launching it orthogonal to the equator. And then that being a great circle, that's going to meet the North Pole right here. But if we launch another geodesic, another great circle somewhere else on the equator, it also launches at 90 degrees, but being on the surface of the Earth, we're guaranteed that it's also going to meet the North Pole right there. So that's a situation where we have two geodesics, they start parallel, but the curvature of the surface forces them to come together. And that I would consider it to be a rather extreme manifestation of curvature. It's enough for the geodesics to start deviating from parallel motion. Whether or not they actually join together, that's besides the point. But generically, if they start parallel, the curvature will force them to either converge or diverge. And that is basically our notion of curvature. That's the intuitive notion that we are dealing with curvature here, unless here, because we didn't have it there. So here we have clearly, a relative velocity that starts at 0 and turns to be negative along the evolution. And we also have a relative acceleration that's always non-zero. So it turns out that the more meaningful notion here is not so much relative velocity, but relative acceleration. Because, in flat space, I started out with geodesics that are parallel, but in fact, if they didn't start parallel, we would still be dealing with straight lines. And we would have a relative velocity between those two geodesics, those two straight lines. But the point is that that relative velocity, in this case, would stay constant. The divergence between the two lines would stay constant in time, therefore zero acceleration. Whereas here, it really changes with the evolution. So in this case, we have zero relative velocity, non-zero relative velocity. But we have we have zero relative acceleration. Whereas here we have non-zero velocity and acceleration. So the velocity aspect turns out to be a little bit incidental. What's really important here is the distinction between zero relative acceleration versus non-zero over there. So if we want to assign an intuitive notion to curvature, it's going to be through the relative acceleration of two geodesics. And we're going to find that it's going to be non-zero in the case of a curved manifold, whereas it's guaranteed to be zero in a flat spacetime. So that's where I'm going with this. So I'm going to turn this mathematical definition into a statement about relative acceleration of geodesics. And we're going to see that there's a direct correspondence between curvature and a non-zero relative acceleration. And what I have to do, of course, is to define what I mean by all that. So what's a relative velocity? What's a relative acceleration? And we have to do this in a way that's properly geometrical, in a way that's allowed to do in curved space-time. And again, I'm going to have to take some time to set this up. If we were working in the flat space-time, it would be pretty clear what we needed to do, right? So if I take that point here to be the point that corresponds to t equals 2, there would be a corresponding point here that corresponds to t equals 2. I would draw an arrow between those 2 points. That would be the relative separation. And then I would calculate the rate of change of this. That would be the relative velocity. Then I would calculate the rate of change of this, and that would be the relative acceleration. So in a flat space, it would be obvious how to proceed because we can draw arrows from point to point, and we can call these arrows vectors. Of course, in curved spacetime, we can't do that. So we have to find a way to translate those ideas into concepts that are proper geometrical concepts. So that's what I'm about to do. And you're going to recognize the construction because it's going to be the same sort of thing that we talked about before. So this 2-parameter family of curves that's going to come back and allow me to do this in a way that's all fine and good. All right. So here's the geometrical setup. So what we want to do here is to describe what happens between two geodesics. And instead of just having two, I'm going to introduce a whole bunch. So we're assuming that we have a vector field U that's a geodesic vector field, and we have the integral curves of that vector field, which define basically geodesics passing through every point in space-time. So we have a geodesic vector field. Call that, how do I call it in my notes? I want to use the same notation. I call it T. Sorry, maybe I'll change my notation here to be consistent with what I was doing before. Oh, let's call it T. And I'm going to assume that we're using proper time parameterization, so I'm really saying that the covariant derivative of this vector field with respect to the parameter, I'm calling it T, but I really mean proper time, that's going to be 0. And because I have a full, I have a vector field everywhere, I really can write this out as this. So the derivative along each curve is a derivative along the vector t, and here I can actually think of all those partial derivatives or covariant derivatives as being defined because my vector t is actually a vector field that lives everywhere. All right, so we start from that, and as I said, through each point in space, time, we have an integral curve of that vector field, so we have a whole continuum of geodesics here. So these are all geodesics. They're all the integral curves of our vector t, and then the vector t is tangent to all of those curves, and I'm using t as an affine parameter on those curves. All right, so all of this is good. So we have that. What I really want to have here is a notion of a separation between, say, this geodesic and that one. And here we have to do it in a proper way without drawing arrows, because we're not allowed to do that unless it's to talk about the tangent of a curve at a specific point. So what I'm going to do here is to introduce another system of curves. And I'm just going to draw them. And the only requirement that I'm making is that I want those curves, those new curves, to go across like that. So those curves I can draw pretty much arbitrarily. I'm not assuming that they're going to be geodesics. I don't want to assume that. So I'm just describing them as curves. And they're going to be parameterized curves like everything else. So there's going to be some parameter that runs along it. So it's a little bit like what we had before, except that I don't have a reference curve and a bunch of variation curves. I just have a bunch of geodesics and then some cross curves that go across them. I could demand that they cross orthogonally, and that would be a handy thing to do, but I don't really need that condition, so I'm not going to impose that. But if that helps, you could think of them as all crossing at right angles if you wish. There's no harm in doing this. It adds a bit of concreteness to the discussion, but I'm never going to use that condition in the calculation I'm about to describe. All right, so we have the geodesics parameterized by t, and we have those cross curves parameterized by s. And then, because we have the curves, we also have the tangents to the curve, and this is something that I'll call s. So those geodesics have tangent vector t alpha, and those curves have tangent vector s alpha. So basically the same sort of construction I've been using and reusing, just applied in a slightly different context, with the one main distinction is that now I have, some of those curves being actual geodesics. Okay, so what's going to play the role of a deviation vector here? The thing that we're not allowed to do in space-time is to draw an arrow, but the next best thing is to use this vector, this tangent vector s, as a notion of going from one geodesic to another geodesic. So we're not actually saying that it points from one point on one geodesic to another point on that geodesic. We're not allowed to say this. But because it's tangent to a curve that reaches across geodesics like this, we can think of this as a meaningful geometrical notion of deviation vector that's going to play the role of describing the distance between two geodesics. And when we take the time derivative of this, or the t derivative of that, that's going to give us a notion of relative velocity, and then one more derivative that will turn into a notion of relative acceleration. So that's how we do it in a sort of meaningful geometrical way. We're not drawing an arrow between 2 points, we're drawing a curve, and then we're thinking of the deviation vector as a tangent to that curve. And so long as those curves, cross across generators, we're fine. That's a perfectly fine notion of deviation vector. So that tangent vector S is going to be what we're going to be thinking as the deviation vector from one geodesic to the next. And the thing that's going to be measuring curvature for us is going to be the second rate of change of that deviation vector. Okay, so those are the essential ideas. I'm going to work out a couple of consequences, and then we'll actually do the calculation. So in these things, it always seems to take more time to set it up and explain what it all means. After that, the calculation is pretty quick and straightforward. Okay, a couple of things I want to mention. So we need a description of all of those curves. So as usual, what we're defining here is a two-parameter family of curves. So we have a two-parameter of curves. So that's very similar to what we did before. So I can describe this in terms of coordinates getting an assignment in terms of t and s. So if we keep s fixed and vary t, something I should have said before that I forgot to mention is that when I set up my parameterization here, I'm going to be making sure that if s is equal to 1 here, it's going to stay, it's going to stay equal to, what do I want to, so if s is equal to 1 here on that geodesic, it's going to stay equal to 1 here, and it's going to be equal to 1 over here. So I want to set up my parameterization in such a way that as I move on a given geodesic, that the parameter value of s is going to be the same, it's going to be fixed. That allows me to say what I was about to say, which is to say that if I move at fixed s, but I let t varies, if I let it vary, then I'm moving along a geodesic. So that defines my network of geodesics. And the tangent vector that's associated with that is going to be the partial derivative of these coordinate functions with respect to t, keeping s fixed. And you know where I'm going with this. I'm going to define the deviation vector to be the other partial derivative, and then we're going to have the Lie derivative property between those two vectors, exactly as I did before. So if we keep t fixed and we let s vary, then the idea here is that, so something I should have said before. So basically what I want to do here is to set up the parameterization in such a way that if t was equal to 0 over here at that intersection, it's going to stay equal to 0 at that intersection, so that each curve here proceeds with a fixed value of t. So we can always do that. So if t is fixed and s varies, then that means we're going across those cross curves over here. We get the cross curves, and then the tangent vector to the cross curves are going to be the partial derivative of those coordinate functions with respect to s, keeping t fixed. So basically, so we define those curves, then we set up the parameterization on them. We can always slide it and adjust it to achieve all of those things so that the cross curves correspond to motion with s, keeping t fixed, and then the geodesics themselves correspond to motion in t, keeping s fixed. And then, I could take the second derivatives, and what we would get from all of this are, I'll go over here. What we would get from that, as we did before, we would get that the Lie derivative of the t vector with respect to the s vector is going to be 0. And that's going to be the same thing as saying that the Lie derivative of the s vector with respect to the t vector is 0. So that comes from the second derivatives being the same irrespective of order with respect to t or s. And if I write this out in covariant terms, we would get that s beta Lie derivative, covariant derivative with respect to beta of t alpha, that's going to be the same thing as t beta covariant s alpha. Right. So basically, I'm using the setup here to justify the fact that I'm introducing a new vector field S that I'm going to interpret as a deviation vector, getting across from one geodesic to another geodesic. And that new, that new vector field that we're introducing here is going to be, Lie transported along the geodesic vector field. So we have that defining equation that tells us essentially what this cross vector field is going to be. So again, so it's exactly the same as what we had before, exactly the same sort of ideas. And we're going to be, proceeding with this, and this equation will be used along the way. So far so good? Okay, so that's the setup. And now we can proceed with the calculation. So the relative separation between geodesics, well, that's going to be represented by our deviation vector, S. So we needed to define it properly in order to provide a meaningful notion of what this means in a curved space-time. If we want a relative velocity between two geodesics, well, what we're going to be talking about here is the rate of change of that vector as we move up along one of those geodesics. So it's going to be the proper, the covariant derivative of that vector in the direction of the geodesic. So I can write it like this, or I can write it like that. So it's the same thing we had here, and at some point I'm going to write it like this instead. And then if we want a relative acceleration, then we would be talking about the second derivative. So I can write it either as, the derivative of the derivative, or I could put that in here, or I could write it all out as T gamma covariant derivative with respect to index gamma of T beta covariant derivative like that. So that's the relative velocity. And after another derivative along T, that defines the relative acceleration. So, so that's what I'm going to use to do the calculation, and but I'm still going to express this as 2 covariant derivative of S with respect to T, and I think that should make it obvious that we're talking about the relative acceleration between two geodesics. Okay, so bottom line is what we have to do now is to work on the right-hand side and try to bring this up to a form where hopefully the Riemann tensor will come out. And that's my promise, that after we're done working on the right-hand side, the Riemann tensor will come out. Okay, so let's go back. So the left-hand side, we're going to express it like this. And then I want to work on the right-hand side. The first thing I will do, I will leave this alone for the time being, but I want to make the replacement between, I want to replace this by what it, by its equivalent in terms of the Lie derivative identity. So instead of writing this, I can write this. And why I would want to do this, well, I hope that this will clarify in a second. Something that will happen, along the road is that we're going to make use of the geodesic equation to kill something and get something that looks simpler in the end. All right, so we have that. I can work through the covariant derivative here. So we're going to have T gamma. And then I'm going to let this covariant derivative act only on S, and I'm going to leave this product all alone. And then this comes along for the ride. And after this, S will come along for the ride, and the derivative operator will act on T. So the second term is going to be T. And then we're going to have the S beta that comes along for the ride. And now we have two derivatives, gamma and then beta, acting on the T vector. Okay, so far so good. I have to look at my notes because I have some choices to make here. Right, so a temptation that I had was to make the replacement here as well. But I'm not going to do that because that's going to take me in a path that I don't want to take. So I'm going to leave it at that for now. What I am going to do here is to change the order of those two covariant derivatives, and that's how the Riemann tensor will pop out. So let's do that. So this I'm going to leave alone. And to get the Riemann tensor out of this, what I'm going to do is to take the commutator between those two derivatives. And then I'm going to add the term that's left over. So this over here will bring me a Riemann tensor. So that's why I wanted to do this. And following the definition here, sorry, get T mu, so I'll write it like that. So that's the Riemann tensor coming out. And then I have a whole bunch of unwanted things because in the end, I know because I looked up in the book that everything else will disappear except for the Riemann tensor term. And in the end, we'll have an equality between the relative acceleration and the Riemann tensor multiplying a few other things. So whatever happens, I have to get rid of everything else. So let's work on the rest of it. I'm going to work on this first. And what I'm going to do here is to throw the T vector inside that derivative. And that's going to be helpful because that's going to give me the geodesic equation and a nice zero. So let me do that. So I have S beta, I have the beta derivative, and now I'm going to throw in the T gamma in here. And now I have something that's zero, that's the geodesic equation, the statement that this is zero. But of course I have to make up for what I just did, so I have to now differentiate the T vector. So I have something left over, and that's going to be S beta derivative of gamma, T gamma, that multiplies derivative of T. Okay, so now it's starting to look a bit better, but we're not there yet, but we're getting there. This is zero because we're dealing with geodesics. We have our Riemann term, but now we have two things that are left over, And I think you're going to see what's going to happen here. Here we have the t derivative of s. Here we have the s derivative of t. So because of the Lie identity over here, those two terms are going to go together. So let's make this work. So
can I have a comment on that equation?
Yeah.
Actually, the meaning of that equation is that it remains zero with respect to change of s. So that expression is not zero because it is the geodesic equation, because it remains on the geodesic curves by changing with respect to s.
Yeah. So what you're pointing out here is that if I had one geodesic among a network of curves, I could conclude that this is zero on one geodesic, but that would be taking the s derivative of that quantity. And if I didn't have geodesics neighboring that one geodesic, the s derivative might not be zero. So part of the setup here was the notion that we have a geodesic vector field so that it's zero not just on one curve, but everywhere. So I can take an s derivative of that, and it's going to be zero because it's geodesic everywhere. So I think that's what you were pointing out. Is that a correct?
Exactly.
Yeah.
Yeah.
That was a correct interpretation. Yeah. So the point is that I need a whole, I need a geodesic vector field that gives me geodesics defined everywhere, at least in that region of space where we're working, to allow us to conclude that not only is the zero on one curve, but its s derivative across curves is zero as well. So that term is zero everywhere. Yeah. So that's a very good point. Thank you for bringing this out. Okay, so let's see. So over here I have, the first term over here and the last term over there are very similar. It's just that I'm naming my indices a little bit differently. So I'm going to do the usual swap of indices. Over here I'm going to rename gamma beta, and I'm going to rename beta gamma. So let's do that. Summing over repeated beta. Here I have a gamma, and here I have a gamma t. And over here, I leave this alone, and I have s beta, covariant derivative beta t gamma. And now those two terms multiply a common t alpha covariant derivative with respect to index gamma. And well, that's precisely the Lie identity we had before. So that's zero, that goes away, and what remains is the Riemann tensor term. And I'll write it, for now I'll write it like this, but I'm going to change this in a moment. So I have t mu, t gamma, s beta. So all I'm going to do, in addition to that, is to just do some cosmetics on this. And let's see, so what I want to do is to re-express the second derivative of my S tensor. And let's see, do I want to put a minus sign there? Yeah, I'm going to have a minus sign. So I'm going to use the symmetry property of the Riemann tensor to interchange those two indices. And that will cost me a minus sign. So I'm going to have R alpha mu beta gamma. And then I have T mu S beta T gamma. So here I have things in the same order as the indices over here. And that's my final expression. So after all the dust is cleared, what we have is a very clear statement that the non-zero relative acceleration between two geodesics in a curved spacetime is in direct proportion to the amount of curvature as measured by the Riemann tensor. So that's why those two geodesics on the surface of the Earth were getting closer together. That non-zero relative acceleration had to do with the fact that the surface of the Earth is curved, and we can assign a non-zero Riemann tensor to that manifold. So it's proportional to curvature, it's proportional to the velocity vector of the curve, it's proportional to the separation vector itself, so it scales with the separation vector. And we get all that, but most importantly, we get this proportionality with curvature. So in a flat space-time, curvature vanishes, the relative acceleration vanishes, guaranteed. In a curved manifold, in a curved space-time, we have a non-zero Riemann tensor, and that automatically gives us a non-zero acceleration. The sign of the acceleration will depend on the sign of the relevant components of the Riemann tensor. So it either can be, an acceleration that pushes closer together, or pushes them apart. That depends on the nature of curvature. But if the Riemann tensor is non-zero, then we'll get a non-zero relative acceleration. And that tells us, the more physics interpretation of this is that, well, it really tells us how to characterize gravity in proper geometric language. So in the old days of general relativity, people tended to associate the gravitational field to the Christoffel symbols. And that had to do with the statement of the geodesic equation. We had the coordinate acceleration being in relation to the Christoffel symbols, and you can interpret the Christoffel symbols as the gravitational force. Well, that's very dangerous, and it doesn't hold up because you can have non-zero Christoffel symbols just because you're using phony coordinates, and that could happen in flat space-time if you're using any kind of curved coordinate system like spherical coordinates. You will get non-zero Christoffel symbols, and you will get terms in the geodesic equation that would have nothing to do with the gravitational force acting on the particle. If we really want to talk meaningfully about gravity, we really have to divorce it from Christoffel symbols, which have, partially to do with gravity maybe, but a lot to do with coordinates, to a Riemann tensor, which now gives us the pure effects of gravity. And the way I like to think about this is, in terms of, here's the Earth, here's me being, released from the International Space Station, feet down, falling toward Earth. And here's my friend over here being released from, a different space station and falling down toward Earth. Because we're in free fall, we might conduct experiments locally that would tell us nothing about gravity because everything in our lab would be free falling together with us. So that's the principle of equivalence that tells us that if I'm freely falling in a gravitational field, locally I don't see anything. Same conclusion here. So each one individually, we would say there's really no effect of gravity because we're both free falling toward Earth. But look at this. We see that our relative separation is decreasing with time. And that's an effect that we wouldn't be able to dismiss. That's an effect that is the true essence of gravity. So that relative acceleration between our two reference frames, or that relative acceleration between the two geodesics that are being defined by those two observers falling down toward Earth, is a measure of curvature, and curvature is a measure of gravity. So, while there was a bit of debate about, how to really characterize gravity in general relativity, whether it has to do with gamma or whether it has to do with curvature, I think now no one in the physics community would debate the issue anymore. We say that we have gravity when we have a Riemann tensor, or non-zero Riemann tensor. And if we have a zero Riemann tensor, we're in flat space, there's no gravity, period. So gravity is in a one-to-one correspondence with the Riemann tensor, and it's really this relative effect of the gravitational field on separated observers like this, each one following geodesics, that is the true measure of gravity, and that is measured by the Riemann tensor. I'm saying this because recently I became aware that philosophers were still debating the nature of gravity, whether it had to do with gamma or Riemann. And I was surprised to hear that, because it seems to me that, for us physicists, and in particular relativists, the issue has been settled for a long time. There's really no need to reopen this. It's a silly debate. The bottom line is we have gravity when we have a non-zero Riemann tensor. And if you have a zero Riemann tensor, you don't have gravity. But you might think that you have, strange effects associated with a strange coordinate system, and those would be, the types of inertial effects that we always see when we're moving in accelerated reference frames. For example, if we were to do our physics on a rotating turntable, we would see all sorts of centrifugal effects that have nothing to do with gravity, but have to do with the nature of the reference frame we're using. So all of that is captured in gamma. None of this has to do with Riemann. Riemann is the true measure of gravity. So it was worth, I think, pointing out those things. So that's the idea. So what we've done here is to go from that mathematical definition that I seem to have lost, where we can define the Riemann tensor in completely mathematical terms, in terms of commuting second derivatives, to something which is physically a lot more meaningful and also much more intuitive, and that's the notion that geodesics will have a non-zero relative acceleration if they happen to move in a closed spacetime. So we go from the mathematical to the more intuitive, still mathematical, but a lot more intuitive, and a much more immediate connection to gravity, because I think, if you see that for the first time in your life, I think you would have a hard time understanding that this measure of curvature has anything to do with gravity, but I think this discussion makes it a lot more clear. Okay, so any questions about this? Okay, good. So let's see. So apart from a couple of extra things I wanted to mention, that pretty much wraps up the discussion on what I call the fundamentals aspects of differential geometry that we're going to be using throughout the course. But I want to add a couple of things that I think are still useful and important, although I don't think we're going to be using any of this in later portions of the course, but I think those are things that you should be aware of and things that are useful to think about. So if we're done here, I'm going to move on to that last little part of the discussion of fundamentals. And next week we'll do more stuff having to do with time-like curves. Okay. Okay, so I want to introduce the idea of normal coordinates, and that's a theme that we'll come back to from time to time. And the spirit is, so there's an approach to do work in GR where you avoid specifying any sort of coordinate system, and you use covariant methods no matter what you do, and you work out relationships between various things based on purely covariant methods without even thinking that there might be an underlying coordinate system lurking in there. And the other approach is, well, find a coordinate system that helps you with your calculation, cut down the computation by a large factor, and if you know that what you're working out is an equality between a tensor and another tensor, you are guaranteed that the equality will be valid in any coordinate system if it's valid in all coordinate systems. So use those coordinates to help you out, no shame in that, and get to your result far quicker and maybe more transparently, and then you're done. So you had a question before.
Yeah, I was just wondering, is there anything, so we have this nice physical interpretation of Riemann, right? What about Ricci? Say you have T and S and contract it with Ricci. What would it?
Yes, so here you don't have the freedom to contract. I mean, you don't have the freedom of making S equal to T, because that would mean that your deviation vector is actually pointing along each curve. So it would, so the interpretation wouldn't survive. So that equation doesn't allow us to extract a Ricci tensor from this and a Ricci scalar, but there are other things that you can do where parts of the Riemann tensor can be decomposed into various pieces, including a Ricci piece and other piece. I think part of the homework assignment has to do with something like this, where we decompose the Riemann tensor into the Weil tensor and then the Ricci tensor and all of this. So that would not be the the starting point of that discussion, because that really involves components of the full Riemann tensor and not necessarily isolating a Ricci part of this. But there are other contexts where this might well happen. There might be spacetimes where the Riemann tensor has a very simple structure, simply related to the Ricci scalar or a Ricci tensor, even Ricci scalar that could happen, but that would be restricted to very specific spacetimes. It wouldn't hold up in general terms. Yeah, Connor?
Just to go along with that, since you sort of brought it up, we want to make this interpretation of gravity being the Riemann tensor, but just for exactly this reason, that we can decompose it into the Ricci scalar, the Ricci tensor, and the Weil tensor. It makes me seem like gravity really is the Weil tensor instead of the Riemann tensor, because that's where all the sources and gravity-like dynamics exist.
Yeah, so people have had those discussions. So if you break down the Riemann tensor into the Weil tensor and the Ricci tensor, if you use the Einstein field equations to argue that the Ricci tensor is really a measure of the stress energy tensor, I mean, they're algebraically related, then maybe you can emerge from that saying that the Weil tensor is a measure of the independent degrees of freedom of the gravitational field, those that are not duplicated by the matter degrees of freedom. You can say these things. In the end, I'm not sure how meaningful it is. I mean, it's nice language and people use that language, but in the end, does it really mean anything deep? I'm not convinced. Typically, the reason why you might want to isolate true degrees of freedom is if you're trying to, quantize the theory, and you have to have, a true measure, a true characterization or, a unique characterization of the true degrees of freedom, and you want to quantize those, but not quantize too much. That might be redundantly related to the other. So there are all sorts of considerations like this where you might want to dig deeper into those issues. But for doing plain old, gravity in the classical world, maybe with astrophysics, objectives, I don't think there's really much there. And all it tends to do is to make people angry at each other because they disagree on things that have no substance, but all, they all relate to different terminology for different purposes. So, but yeah, I mean, that's my humble opinion. Others might violently disagree and say that it's perivative. It's imperative that you would do this, but I choose not to. Okay, so let's see. Right. So the theme is, if it helps you choose coordinates that simplify a calculation, and then, rebuild the covariant result after the fact, that can be a big time saver in doing various calculations, and there'll be lots of examples of that in the course. So I want to introduce Riemann normal coordinates. And I don't want to go over time this time, so I think I'll just throw in a couple of ideas, and I'll save the rest of the discussion for next time. But I just want to introduce the ideas first. So the basic idea here is that a curved manifold, even if it's curved, is still locally flat. So look at the surface of the Earth, look at the classroom over here. We would be hard pressed to find any notion of spatial curvature on the scale of this classroom, given that the curvature manifests itself on the scale of the Earth itself. So locally, any manifold will look flat. And the idea is very intuitive, but sometimes we need to make it more quantitative. So how do we decide if a given patch of a curved manifold is small enough that we can ignore the effects of curvature? Well, there's a way of doing this. And there's a way also of coming up with a coordinate system where at a reference point on any curved manifold, the metric there will be Minkowski, and the Christoffel symbols there will be 0. So there's a way of achieving all of this, and all of this captures the idea that a curved manifold is locally flat. So what it means, in precise terms is this. We can always pick a P in space-time, and that's going to be our reference point. And remember that a point in space-time here is a point in space at a moment of time. So we really pick a moment of time and a position in space. So here's our point P. And the idea is that there exist coordinates, and here I'll denote them x mu, such that the metric at that point in those coordinates is precisely equal to the Minkowski metric. So -1 + 1 + 1 + 1. And the Christoffel symbols at that point in those coordinates is precisely 0. So those are all statements that refer to that coordinate system where the statements are true. And another way of stating the second property is that at that point, the partial derivative of the metric can be set equal to 0. Can we impose more conditions? Can we say anything about second derivatives? The answer is no. We have to stop there unless the manifold is flat. We're dealing with Minkowski spacetime all along, and in which case the metric would be globally everywhere Minkowski. But that's where it stops. We cannot also impose that second derivatives of the metric at that point be 0. That wouldn't work. So that cannot be. But we can always impose those conditions, which tells us that in a very specific sense and very meaningful sense, we're dealing with the Minkowski metric near that point. We're dealing with a situation where near that point the Christoffel symbols are 0. The only thing that we cannot turn off is the second derivatives, because those are going to be related to the Riemann tensor, and the Riemann tensor at P is not equal to 0. So that statement has to do with the fact that the Riemann tensor at P in general will not be 0. If it happens to be 0 at P by some happy accident or whatever, then yeah, sure, we could impose more conditions. But generically speaking, when you're dealing with a curved spacetime, there's curvature everywhere. There's at least one component of the Riemann tensor that's going to be non-zero everywhere. And so what I should say is that at that point P, there's at least going to be one component of the Riemann tensor that's not going to be 0. And that prevents the imposition of more conditions. So there are lots of ways we can construct coordinates to achieve this, and they tend to be not terribly meaningful, but there's one set of coordinates that turns out to be geometrically very nice and correspond to things that are very nice and geometrical, and those are the Riemann normal coordinates. And next time I'll go back to that and describe how they're constructed. But the point that I wanted to make, and that's to make, to go back to the theme of using coordinates to help yourself, there are lots of calculations that sometimes can get very laborious because you have to keep all sorts of Christoffel symbols in the calculation so that in the end you end up with combining them with partial derivatives in such a way that they give you covariant derivatives. And if you keep track of all those Christoffel terms along the multitude of steps that you have to go through in a calculation, it can get very tedious, and you can make mistakes, and it can be, really bad. So the idea is, well, why not appeal to a coordinate system like this, where at a point you can get rid of the Christoffel symbols altogether? If you just choose to do this, and you can always do that, you can make that choice, you can, work in a coordinate system where at a point you don't have to worry about Christoffel symbols because they all vanish at that point. And then you can do your calculation, forget about all the gammas because they're all 0, and then in the end you end up with a result. And if your equation is in the form of a tensor is equal to another tensor, That equality might have been established in that very specific coordinate system, but if you have an equality between a valid tensor and another valid tensor, that equality will be guaranteed to hold in any coordinate system. So if you can establish this equality easily in that coordinate system, while I say do it, save yourself some work and trouble, establish the equality in that coordinate system and the equality involving valid tensors, you're guaranteed, you don't have to justify that, you're guaranteed to have a perfectly well, to have the same equality holding in any coordinate system. So that's a way in which you can save yourself a lot of work. I'm not sure if we'll encounter these kinds of situations in the course, but there'll be different situations where we're going to pick a coordinate system that will save ourselves a lot of trouble because the coordinates have been adjusted in just the right way to suit the purpose of a calculation. And my philosophy in life is do it the easy way if you can, because it's harder to do it the hard way. So, make yourself, do it the easy way if you can. It's a lot better than this way. Okay, so we'll stop here, and next time I'll talk. So here, that was just the idea that we can impose those conditions by choosing the coordinates. What I'll tell you next time is how to build the coordinates so that we have this satisfied. Okay, so enough for today. See you.